Now, what is percentage purity? Um, Percentage purity is when we're just looking at how pure a substance is. And the formula for percentage purity is mass of the pure substance, mass of the pure substance over the mass of the impure substance. I think we might have discussed it before, but it's fine. So this is how we calculate percentage purity. Mass of the pure over mass of the impure. So what is it talking about? In, let's say, chalk, right? Chalk is made up of calcium carbonate. Okay? But then chalk is an impure calcium carbonate. Chalk, we call it an impure calcium carbonate. Why do we call it an impure calcium carbonate? Well, this is because inside chalk there are other substances which are not calcium carbonate. I'm sure you've seen that if you take a chalk, right, it has those kind of like what do they call them? Those holes that show you that there is a bit of carbon dioxide that was there and stuff. So the thing is, when they were making chalk, right, other substances apart from calcium carbonate, they penetrated through. You understand? So while they were making chalk, it means other substances, they penetrated inside there during the production of chalk. So because chalk doesn't only consist of calcium carbonate, we say that it's an impure calcium carbonate. Okay, so that is an impure substance there. It is a substance which has impurities inside. When we say impurities, we mean that it has foreign substances that are not the one in focus. Okay. You would hear this, they will talk about lime. They can talk about limestone. Still, similarly, it's an impure form of calcium carbonate because when they make, because in there will be other substances which are not calcium carbonate. So you should just think of any impure substance as a substance which has um, impurities. But then those impurities, in most cases, they are in less quantity compared to the pure substance. So when you look at chalk again, right? When you look at chalk, majority of chalk. So this is chalk. Majority of the substance that make up chalk is calcium carbonate. So in that way, since it's the majority, the smaller minority substances, those are what we call the impurities. So if we wanted to calculate the percentage purity of this calcium carbonate, we would say the percentage purity will be the mass of the pure substance of calcium carbonate over the mass of the chalk, or the impure sample, the impure calcium carbonate. Then you times that by 100. Then you're gonna get percentage purity. The higher is the percentage, the better is that substance, because usually we prefer pure substances. So the more the percentage, the more pure the substance is. The less the percentage, it means the less pure the substance is. So that is what we mean there. Now we can have a lot of calculations or questions that are based on this, but the basic understanding, it lies on knowing what is an impure and then what is also a pure substance. Right. So let's make an example, or rather, before we go to an example, please note that when we give you if I were to give you a reaction like this, magnesium Sa plus calcium carbonate give us magnesium a salt plus a metal plus a metal carbonate is salt, carbon dioxide, and yeah, okay, so it's gonna be CO2. What compound are we gonna form here? MgO. We must have MgO. Yeah, we must have MgO plus carbon dioxide. Let's just say also plus calcium oxide. Nay. So as an example, what I just want to emphasize here is that this calcium carbonate that you see here, do you think it is chalk? Do you think it's the pure one or the impure? Please let me know that. You can type it out. Do you think that that calcium carbonate is a pure substance or impure? So they tell you that 50 grams of impure calcium carbonate reacts with magnesium. So what I want to understand is that since you are given this statement, okay, what I want to understand is that this calcium carbonate I'm seeing on the reaction, is it the pure one or is it the impure? Meaning its mass, is it 50 grams or not? Please let me know there. Let me know if you think that is a pure or impure substance. You are told in the instruction that 50 grams of impure calcium carbonate reacts. Right? I see Mr. Kevin is saying impure. Right? Then I see others. So anyone else? So think that is impure, or do you think it's a pure substance, the one in the reaction? Okay, no problem. Yeah, so that is not an impure substance. This one actually is the pure substance. Okay, so the thing is that why is it the pure substance? If you take chalk and it reacts in a reaction, the impurities are not going to react. Okay, the only thing that is going to react is the pure calcium carbonate. So in this impure sample, it's only the pure part that is going to take part in the reaction. You understand? So please know that as we're gonna look at questions there, please know that this 50 grams is actually the mass of the impure sample, but the mass of the pure is the one that you calculate on the reaction. Just like remember when we said that we have theoretical mass and actual mass in a percentage yield, right? Remember we said theoretical is the mass that you calculate on the reaction, right? So think of theoretical mass as the pure sample. Okay, So the pure sample is the one that is going to take part in the reaction. So just take note of that, as we shall see in the questions that we're gonna do. Let me give you a question here so that you can see how the questions are tackled and how the questions are asked. Okay, let me show you here. Okay, copy that. So here's a question. Right. Here's a question, and then let's see how do we deal with this. So you are given that a sample of impure calcium carbonate, which is limestone, right, of unknown mass, required a continuous supply of strong heat to decompose it into the following reaction. So here's what is happening. We have an impure sample, right? We apply heat to it so that it decompose, and then it decompose into calcium oxide and calcium dioxide. Not calcium, sorry, carbon dioxide. Okay, calcium oxide and carbon dioxide. That is what we produce when calcium carbonate decompose. So after completion of the reaction, it was found that 11,76 grams of calcium oxide was produced. 11,76 grams of CaO was produced. So this guy, we know that the mass of that was, let me write it here, the mass of calcium oxide was equal to how much? 11,76 grams. Okay, remember this is a product. Remember, whatever is on the right is your product, and then whatever is on the left is gonna be the reactant. Whether it is one or whether there are 2, 3 or 4 or 5, what is on the left is the reactant, what is on the right is the product for the forward reaction. Okay, so the percentage purity of calcium carbonate is found to be 80%. Calculate the mass of the impure calcium carbonate. You see, it's a very beautiful question. So when we write it, right, if we were to write it, we say percentage purity is equals to the mass of the pure sample pure substance over the mass of the impure substance. Then what do? We multiply that by 100. Now in this case, percentage purity was already given that it's 80%. So what do? We go to the formula, you substitute 80. Please don't substitute 80%. Please don't write it as 80 over 100. Please just put 80 there. Okay, and then the mass of the pure substance, do we have it? No, we do not have it yet. So to make it easy, I'll just write M of pure, and then M of impure we also don't have, times by 100. This is how you substitute the percentage purity. Even if it's percentage yield, you just write the number there. You understand? Now that we have this, our challenge now is that we don't have the impure, and then we also don't have the pure. Well, the pure, do you remember that I told you that you can take it as the theoretical, in percentage yield, we used to call it theoretical mass, the one that you calculate. This one we shall call it, it's also theoretical, because the pure part is the one that take part in the reaction. It's only the pure part. So let's go back to the reaction and say, all right, we have CaCO3 producing CaO plus what? CO2. Now the mass of this guy is 11,76 grams. Now we can convert this mass into what? Into number of moles. That one you know already. So we can say number of moles of the CaO, calcium oxide, is equal to the mass over the molar mass. Now the mass is 11,76 grams. What is the molar mass? For calcium, I think it's 40. For oxygen, I think it's 16. Ne? Can you just confirm that for me? Is that correct? Okay, let me just take a paper 2 here and confirm. Yes, sir. Yeah, CaO. Oh, great. So indeed, calcium is 40, that is 16, so we get 56. So the number of moles that we get there, right? If you were to quickly punch that in your calculator, do we get 11,76? 11,76 divided by 56. Don't we just get 0,21? Okay. 0,21 moles. All right. No, that is fine. That is fine. But remember, that number of moles there, those number of moles, is for calcium oxide. Now we need to get the number of moles of this guy, and you know, if you want to get number of moles of that guy, we use a ratio. So we're gonna say the ratio of CaCO3 is to CaO, yeah, is 1:1. So therefore it means the number of moles of calcium carbonate will also be 0,21 moles. But we need the mass, right? So let's convert those moles to mass. We use the formula N is equals to M over molar mass, 0,21. We are looking for the mass. Now for calcium carbonate, remember you're dealing with 40 plus 12 plus 16 times 3. What does that give you? It's 100. So therefore the mass is going to be equal to 21 grams. But this is the mass for CaCO3, right? For calcium carbonate, that is the mass. But is this mass belonging to the pure sample or the impure? Let me know. Is it the pure or the impure? The one we just calculated, is it for the pure or the impure calcium carbonate? The pure. Why the pure substance? No. The reason is not because we are looking for the impure. The reason is because it is the one we theoretically calculated. We calculated it. It's the one taking part in the reaction. It's not an impure sample that will take part in a reaction. It's only the pure part. We use the impure sample, but it's only the pure part of that sample that is going to react. So therefore, what we calculate there on the reaction is the pure sample all the time. Do you understand that? Great, great. So it's the pure sample there. So we can therefore say 80 is equal to the pure sample is 21, but then we then look for the mass of the impure sample. and then we multiply that by 100. So obviously now you need to divide by 100 both sides, so that you have 0.8 is equals to 21 over the mass of the impure. So these would cancel. Then from there you can solve for the mass of the impure by cross multiplying. So the mass of the impure should be 21 over 0.8. 26.25 grams. Nay. 26.25 grams. So that is it there. That is the impure sample. And as you can see, it is quite larger than the pure sample, because our pure sample was 21 grams, the impure is 26. That's how it works there. Then you get your 6 marks. So just to repeat, right? We have a sample of impure calcium carbonate of unknown mass, which is decomposing to form CaO and CO2, carbon dioxide and calcium oxide. However, let's understand that even though the heat is being applied, to the impure sample, it's only the pure calcium carbonate that is going to react. So we do know how much was produced for the calcium oxide. We know the mass of calcium oxide that was produced. So we use that mass here that was produced to convert it to moles, and then we then get moles of the calcium carbonate. Then once we have the calcium carbonate, the moles, we have to understand that we got the pure moles. So you convert those pure moles to mass, and then be able to get the percentage purity. Any question up to so far? Are we getting it? Are we? All right. I had another one here which was talking about, yes, here we go. Let's see this one. It's difficult to take this, but let's look at this one. Now give this one a try, or rather let's just walk through it and see if we can be able to solve it. So here they tell you that 15 grams of impure magnesium hydroxide was reacted with excess phosphoric acid to produce 16 grams of magnesium phosphate, as you can see there, according to that balanced reaction or equation. 4.1 says calculate the percentage purity of the magnesium hydroxide. So now you start to analyze the question. That's the first thing you want to do, analyze the question. We are told that it's 15 grams of impure magnesium hydroxide. Let's go to the formula of percentage purity. Percentage purity, remember, it's the mass of the pure sample over the mass of the impure sample multiplied by 100. Now, do we have the mass of the pure sample? We do not have, because usually the mass of the pure sample, we need to calculate it. This one, we need to calculate it theoretically. Calculate using the equation or the reaction. That's how you get the pure sample. What about the impure? Usually they give you if you have to calculate the impure, ne? Just like you see the one we did before here, you needed to calculate the impure because it wasn't given. It was a sample of impure calcium carbonate of unknown mass. Ne? So what we did is that we calculated the pure sample, then we could simply substitute it and solved for the impure. Now here, the impure is given that it is 15 grams, you understand? So because it's 15 grams, we simply say, that is very nice. We already know that here it is 15 times by 100. But now, the mass of the pure substance we do not have. We need it. How do we get it? We need to calculate using the reaction. So, we were told that the magnesium hydroxide was reacted with excess phosphoric acid. So, this tells us that our pure sample here is actually the limiting, and this guy here is actually the excess reagent. Please remember that. That is how we can tell you that this thing is the limiting and that one is the excess reagent. So we're told that we produced 16 grams of magnesium phosphate. So this guy, we know that we produced 16 grams. So remember, what can we do to that mass? We can convert it to moles, isn't it? So that is the first thing we want to do. We want to convert that mass into moles. So we say number of moles is equals to mass over molar mass. Now, the mass is 16 grams. So here we're talking about the Mg3PO4. Now, its mass is given as 16 molar mass. Now, we need to calculate or add, right? For magnesium, we're gonna say what? For magnesium, we would say, where is magnesium? Magnesium is 24. So please say add 24. You see here there is a times 3, ne? You multiply by 3, then you say plus. Phosphorus, which is P. When you go to your periodic table, phosphorus has a mass of 31. So you're gonna say 31 plus, for oxygen it's 16. You're gonna say 16 times 4. However, don't forget to multiply everything by 2 because of these 2. You understand? So you have to multiply that bracket by 2. Don't forget to do that. So now what do we have? We're gonna say therefore the number of moles there is gonna be 16 over. Now if we say 24 times 3, and then we say plus 31 plus 16 times 4, and then we say all of that times 2, we get 262. I hope you're also getting 262. Is that what you get, sir? Okay, so you get the moles to be 0,0611 moles. We don't have to round off, remember, because it's not the final answer. So we have to write all those 4 digits. Okay, then now that we have the moles, we can then use the ratio, right? The ratio. So that ratio is going to be for magnesium phosphate with our sample, the pure one. We're talking about MgOH2. So this one, okay? So my goodness, okay, hopefully it's gonna show. All right, so we're gonna have to say number of moles of is it Mg3 PO4, right? And then we put a 2 there, is to the number of moles of that magnesium phosphate. Okay, no, already that's the magnesium phosphate. So we say MgOH2 OH2, which is this guy here. That's the pure sample, isn't it? A ratio there is it's 1:3. Ne. So for magnesium phosphate, the moles we got to be 0,0611, and then here we don't know the moles, so you can just simply cross multiply there, and then you'll have 3 times 0,0611, which gives you 0,0611 times 3 gives you 0,1833. Those are the moles for the magnesium hydroxide. So we just have to change the moles now to what? To mass. So we know that we use the formula N is equals to M over the molar mass. Now the moles is gonna be, yes sir, you forgot the zero, sir. You see it? Okay, no problem, no problem. Yeah, just be careful there. So now that we have the moles, we can put them here, and then make sure that we get the mass. But the mass we are getting now is for the pure magnesium hydroxide. Okay, that's the mass we are getting all over what? The molar mass. All over the molar mass, because we are using this formula. Ne? So molar mass of magnesium hydroxide is gonna be, for magnesium is 24, plus for oxygen is 16, plus 1, and then you multiply that by 2, right? Multiply that by 2, and so remember, this is the mass of the pure sample, the one that take part in the reaction. So you're gonna have what? 24 plus 17 times 2, get 58. Therefore the mass of the pure substance, it's gonna be what? 0 times 10,63 grams. Therefore the percentage purity now is gonna be the pure one 10,63 over the impure. Remember, the impure you're given is 15, then you multiply by 100. So you say 10,63 divided by 15, then you times by 100. 70,87%. So that is the percentage purity there. Did we follow along? Did we get it? Okay, no, that is great. So if you can just remember for me that the pure sample is the one that take part in the reaction, then you're okay. The rest is easy, because you're just using stoichiometry to get the mass of that pure sample. Because in most cases, all the time, you'll have to calculate the pure sample. All the time. The impure can be given or not. If the impure is given, you need to calculate percentage purity. But if the impure is not given, then you will be given the percentage purity, which is the same as when you're dealing with percentage yield. If I give you the percentage, I might need you to get for me the actual mass, because I know that the theoretical you'll always be able to calculate on the reaction. Then if I give you the actual mass, then I might need you to get for me the percentage yield. So you understand that it's either you're given the percentage or the impure, or you're given percentage, or you're given the actual mass. That's how these formulas work. They're very much similar. So hence I'm making a link between them. But this is what we do. If you are given the pure the impure, then you have to calculate percentage purity like we did here, right? But then if the impure is not given, then the percentage must be given. That's how it works there. So quite easy, I hope. Now next questions there is asking, the questions are asking, if 20 grams of the same impure was used in the above reaction, how will each of the following be affected? So what they are saying is that, let's say we didn't use 15 grams of the impure. Let's say we used 20 grams more of the impure. How will it affect the following? Number one, the mass of this that is produced. Would we produce more mass, meaning the mass, would it increase, decrease, or remain the same? What would you say? If we used more of the impure, our products, were they going to be more or less? Mm-hmm. Yes, that's correct. So it's gonna increase. It's gonna increase because you are using more. Um, you're using more of the what? You're using more. You have more of the impure, which means you also have more of the pure. Therefore, you're gonna produce more of the product. You see, that's how it works. And then, what about the percentage purity? Was it gonna increase or decrease if you have more of the impure? Mm. Mm. Uh, did I? Oh, sorry. Ish, it's yeah. No, yeah. Please continue. Sorry, this was a mistake there. Okay. So I see the basis of your explanation. I think you are saying that because we said in 4.2.1 the product will increase, that means the pure sample will also increase. And if the pure increase, then it increases percentage purity. That's what you are saying. Eh, eh, em- Okay, but the problem is that even though the pure is gonna increase because the product, we said we have more product, but the impure also increase. So both of them, they're increasing at the same rate. Understand? So because they're gonna increase at the same rate, it's not gonna affect the percentage purity. It's gonna remain the same. Yes, it's gonna remain the same, and mainly it's because um, the ratio ne, is because the ratio of the pure to the impure, the ratio of the pure sample to the impure remains the same in a given total mass. Remain the same. So that's how you would explain it there. Is that the ratio of the pure to the impure is going to remain the same because they're going to increase at the same time. So they are not having an effect on each other, because the more impure sample you have, the more pure sample you also have. So the percentage purity is going to remain the same. Is it clear? Yeah. So that is how you would answer that. And that is the two ways in which percentage purity can be asked. So it's either you are calculating percentage purity, the percentage, or you are given the percentage and then you have to get the impure sample. And then, yeah, that is about it there. Not if, um, yeah, that is about it there. Is there any question? So if I can send you a question, we can be able to answer it. No, I trust you. I trust you. So what I'll do, I'll send a question right now in the group there, and then just you can write it and then send me a picture there, snap. Then I will mark it. Is that okay? Okay, no problem then. And then if you get dates for any of your SBAs, please tell me so that I know in advance and we can prepare. Okay.